I don't know. I am not sure. Alright, there's Nick. I noticed a general, let me check the submissions on the homeworks, because I was actually trying to look at those this morning and several people hadn't gotten to them yet. Okay, there's another one. So Devin should be here since he finished it 7 minutes ago. Okay. Well, almost everyone is here now in at least Discord. Rippy has yet to join the live stream chat, but he is in the Twitch chat, so that's all we need to see. All right, cool. So topology, let's do it. I did want to talk about one option first. So basically, yesterday had some technical difficulties with Calc 2 just because Twitch, I think, like had a bad spike or something around my class time, and it was just like buffering the whole time. It's like the first real issue I've had outside of a Hearthstone stream as well on Saturday, but I use Zoom as like my escape route, and essentially I just wanted to like give you guys the option. I think for that class, Zoom makes a lot more sense because they went from very talkative in class to very, very silent with this setup. You guys, though, are pretty good at participating and stuff, and I feel like things have gone fairly smoothly. But I wanted to at least give the option, so I'll probably send out maybe like a little doodle poll later on whether you would prefer to go to Zoom or stay with this setup. You know, the benefit of Zoom is that it's live. You know, there would be no 7-second delay. Drawback, if you aren't speaking up, then chatting is much more, I think, cumbersome in Zoom than it is on Twitch. And the recording, I need to figure out a little bit because I don't want to have your pictures on the videos if I want to end up posting them to YouTube. I feel like that would be, even if you said it was okay, it still feels like more than I want to do. I don't really want to just like have you guys hanging out in your rooms at home doing class and being posted on YouTube. So I'm pretty sure I can do just my share screen. I just need to figure that out. So just the one like logistical order of business that I wanted to discuss, and we can talk about it after. I have office hours, you know, a lot today, so like 11 to 2 and or 11 to 12, and I can be free like 2 to 4 as well. See Devin typing. Might be able to use Snagit to only capture. I will look into that. Thanks. Yeah, I've never heard of that before, so I will check it out. Okay, so quotient topology. I was looking at some of these before class, and I mean, yeah, I see some right ideas, some wrong ideas. Well, I think part of the goal of going to Zoom right is that I could see you. I think that would be kind of counter intuitive to go to Zoom and then just turn your camera off. Okay, so 177 is one we talked about a little bit last time, at least in terms of like what the picture is, but we didn't really get into the meat of it, which is like what are our open sets. So here, right, our starting interval is this guy, and you can assume, right, like the standard topology on this, so the subspace topology inherited by your standard guy on R. So basically open intervals, except you can add the endpoints 0 and 1 as well. And then essentially we're just gluing 0 to 1, and I don't really know, I'm going to change this in the future editions of the book. I say from 0 to 1 here. I mean, really, I think it should be all of these, or just left off completely, because we want an equivalence relation, right? And so if it's an equivalence relation, then it's reflexive. So this is just redundant. Everything is always going to be equivalent to itself if we're talking about an equivalence relation. So yeah, I'm not sure that really even needed to be stated. But the point was, right, we take our interval and we're saying that these two guys are equivalent, and so that leads us to the circle where those blue guys are glued together. So then the question is, what are the open sets? So this is our x, and then this is our x star, right? Our quotient space. But if I say quotient space and not just like a quotient set, I mean I'm saying there's some topology on this, right? The quotient topology. So like, what is this? And I gave a hint as to look at two different things. So look at, I guess I need to define E first, right? So E is just the set 0, 1. Essentially, you might assume that the one place where we're doing gluing or changing our space is the one place where we may have weird stuff going on. So just define this set to be E, and then essentially look at U as a subset of X star. What happens with, right, this is like our map P, P inverse of U if U intersect E is empty or non-empty, as our two different cases. So what did we find out? Is there any difference between these? Like, what's going on here? Right. So what I'm seeing here, if you look at this blue interval, then this looks something like 0 to A, union B to 1. And that is open, right? This is, so P inverse of U is equal to, and this is open in the subspace topology on 0, 1, right? Is this the only case? So right now what it looks like is, well, this guy was open to start, and of course I could have closed off these things, and basically it would have been closed off then in the pre-image, and so not open. So essentially we see that we're just getting like the open intervals go back to either an open interval or a union of open intervals. So it seems like maybe it's just the subspace topology somehow, or just kind of viewing it as like the subspace of R2 here, right? That little arcs, open arcs or unions of open arcs are going to be our open sets. Can anything weirder happen? There's maybe one case we're not considering here. Yes. It is, right? Because this is equal to P inverse of, so just do a half open guy, right? So just take this, and it would be, I see. No, you can't get just that. You would get union 1 is the issue, right? So that's the problem here. So you're right, we can't quite do it. Right, right. And so, yeah, you can try to include that point, but then you also have to include this guy, and we've talked about before, right? So like, yes, we can include the endpoint, but we have to include like some little piece before it, right? So it's like some little 1 minus epsilon to 1. So yeah, I actually think this is all we're going to get. Yeah, so you can kind of view this as subspace topology of R2. I think we just did the open interval over E. Oh, sorry. Yeah, you're just responding to Rippy, not me. Okay. Okay. Yeah, so that's kind of the idea. You just kind of want to think backwards, like what are the open sets here? How is it translating back via the pre-image, right? And it just takes some getting used to in terms of going backwards. Yes. So right, this guy is not open in the quotient. See you type in Rippy. So wait, to clarify, our open sets are only open intervals. Open arcs on the circle. So yeah. Let me conclude then. So open sets, yeah, in the quotient are open arcs or unions of them. Yeah. But none of them contain the endpoints. Correct. Right. Because the only endpoint that you would be allowed to include up above would be 0 or 1. But our only way to do that here, you have to include both 0 and 1. And then you would need an open piece around that. Yeah. Okay. Good. So then we had this guy. Now this one, I think a lot of people at least figured out like what should be equivalent to each other, but maybe not the quickest way to see like what it glues to. So here, right, it's if you have an integer difference between two numbers, they're equivalent. And so I was talking to someone yesterday, and they're like, basically that means that like everything after the decimal point is equal, right? So if they have everything past the decimal point equal, then they are equivalent, and so you glue them together. So what like common space or what is a nice compact way to write this? There are many ways to do this, but yeah. Okay, yeah, so we've got the interval from 0 to 1. Is it the subspace topology? Or subspace topology, like you mean from R? Uh, say that again, Nick. Right, so here you would look at, yeah, right, exactly, instead of with that close point. Okay, can you explain why it's the subspace topology? Okay, so let's look at pre-images after, we answer Rippy's question. So why 0 to 1? Doesn't it work for like all of r greater than 1? It actually just works for like any, I mean, I could do, and really I could do the right point included as opposed to the left, but I mean, you can do, actually, I guess it doesn't have to be an integer either. I mean, you can really just do this or this for any x in R. We just tend to think about things near 0. I don't know, like our unit circle, our unit square, we just kind of focus ourselves in at 0. Yeah. And maybe one other thing. So what is our actual map here? We can actually define like a very real function. So like p of x equals something. Nick, I think you had a pretty good explanation of this. Yeah, good. Right, so this is our quotient map. Right, it's clearly surjective. Is this a projection down to a number? Yeah, pretty much, right? I mean, you're projecting down to you're projecting onto the decimal portion of your number. Yeah, it's kind of how you want to think of it. And so, I guess my issue here is the endpoint, right? So let's consider p inverse of 0 to 1/2. This is going to be the union of n to n plus 1/2 over all n and z, right? Is this open? Yes, I guess. Yeah, right. Oh wait, going all the way down. No, it's not. Sorry. Because of these endpoints, right? I was about to trick myself just because we are going back to negative infinity, but no, I did come up with this for a reason, right? So like this guy is not an open set. In R, right, you're just looking on the real line, you just have a bunch of things that look like this spaced 1/2 apart. And so including these endpoints is an issue. So it's not quite the standard topology. It's basically, again, all of the open intervals, but 0 is an issue. So open sets are, open intervals are unions of them. So unions of open intervals inside 0 to 1. So not quite subspace topology. Why would be x minus the floor of x? Don't we want the result to be in z? No, so that's how we define the equivalence, that their difference is in z. So what we're saying is equivalent is that x and x minus the floor of x are equivalent here. So, right, what I'm saying is x is equivalent to what it maps to, which is x minus the floor, and that's because x minus the floor is equal to the floor, which is in z. It's a good question. Cool. Does that make sense as to why this isn't the subspace topology exactly? This thing here? So if we take a half open interval that just isn't the whole thing, that's all I need, then, whoop, we gone. Okay, we're back. Then you're going to get a union of things that look like this as the pre-image, right? Because all of these guys go to 0, all of these guys go to 1/2, and in between, right, you just get this half open interval. And the union of this is the preimage in R, but this is not an open set of R. And so, like, by definition of our quotient topology, right, a thing inside 0, 1 is open if and only if its preimage is open in R. And here, this preimage is not open, so this set is not open. So we can't do the things including 0, which would be open in the subspace topology. Is that more clear, or do you have a specific question? Come back. I came back. Yeah, I think it does take some practice. For me, I'm always looking at like the endpoint, right? Because like open intervals are going to like unions of open intervals, and that seems fine. The issues tend to happen at the endpoints, because that's where the subspace topology is like interesting, right? That we can suddenly include endpoints where we couldn't before in R. And so I looked there, and I see that okay, if I take the preimage, then this is an issue because I'm including the endpoints in R where I'm not talking about the subspace anymore, right? And so their endpoints are bad. All right. So then 179. Yeah, I like this one. This is a very useful one in life. Rays are very important. You can talk about the visual boundary, and it's very exciting. All right. Anyway, so here, right, we're very much talking about the equivalence relations. I'm not even defining you a map. I mean, I guess that's kind of been true on the other ones, but maybe the map was easier to see. So here, right, our picture is we've got the origin in R2, and then we're just taking all of the rays emanating from it, right? And these are all different equivalence classes. So that means when we're gluing, all points on a single ray get glued together. Right, when we're taking our quotient. So all of these guys are equivalent. So, let's do a simple ray where I can easily write all the points along it. Take your positive x1. So for instance, the ray x0, where x is greater than or equal to 0, is a ray. There's an A in there. So this means that x0 is equivalent to y0 for any x and y bigger than or equal to 0 here. Right, so any guys along this ray would be glued together as just like one point. So basically, in your quotient topology, you're viewing each ray as a point. And then you want to see, like, what does that form? Anyone figure out what this is? First of all, headphones or mute, yeah. So you could, right. Oh, yeah, I should have said just greater than 0. I forgot. Yeah, we are. Oh, no, that's not great. Yeah, we're deleting the origin there, is the point, because you don't want them all to be equivalent to each other because of the point 0. So yes, strictly greater than 0 and strictly greater than 0. Right. All that matters is the angle. So yeah, Jack, I think that's maybe what you were getting at when you said use polar coordinates, is that what you really care about is your angle here. And basically for any value of r, they're the same, right? So, r1 theta is equivalent to r2 theta for any r1 and r2, right? If they're both positive. Otherwise you're going, well, yeah. going in that direction. You're fine. Right. And so, yeah, you do get like S1 cross S1 or the circle, and usually we just do like the unit circle. And so, polar space with R not equal to 0. Yeah. Yeah. That's one way to think of it, pretty much. But again, you're gluing. It's still a quotient of that, right? Like you're still gluing all of these things with the same different radii in the same angle. So essentially, I just see that every ray passes through the unit circle, and I'm just picking the points on that unit circle to be my representatives, right? My equivalence class. And so, right, as you said, like there's no origin, so it's got to be a circle of positive radius is all that you really need. And I don't think many people would call a point a circle anyway, but yeah. Right. Okay, true. Yeah, you have to be careful with theta. I guess I was assuming that we were in 0 to 2 pi. He is my former office mate. Just hanging around, enjoying topology. Yeah, so I was working under the assumption that we had theta between 0 and 2 pi, but that's a good point. Any questions on this one? Enjoying topology, Kappa. Okay, so what are our open sets here? So, what does a pre-image look like? This may be harder to picture. Any thoughts? So if I say, I'm taking this as my circle, and I want to know, like, okay, so let's look at, like, what is this thing? Well, theta r with no restriction tells me not much. That seems like it could be all points. Or a point? I don't know. So what is the pre-image of this? So if I call this, u, what is P inverse of u? Well, I'm basically taking all of these rays, right? Each point here corresponds to a ray back in my space. So if I do P inverse, right, I'm like lifting back up. This is weird because I should probably go, this is going up to R2. And now I'm basically taking all of the rays. I'm just going to draw the ones that I don't have, right? So it's like, this is my dotted line, this is my other dotted line, but then I get all of the rays in between. Yeah, so it's an infinite pizza slice. Yeah, that's a good way to think about it, except for like we're not including the edges, right? And so this is an open set inside R, basically because it's defined by like strictly greater on this boundary and strictly less on this boundary, right? And you can actually strictly define these. These are lines, right? So you could say just like y is greater than whatever this is. Not exactly with the cross comma. It's on the sides. But yes, so these are definitely open. So it looks like this. So yes, this is definitely open. What if we include, so remember, we're not including 0, so it's always open down here, right? There's like this hole at the end. What if we do include an endpoint on U? Would that be open? Because I still have this like gap down at the middle, down at the origin? What do you think? All right, can we stop memeing? So what if I have this piece included, for instance. Yeah, you're right, Jack. It's not. And again, like, yes, it has an opening down here at the origin, but the issue, right, is you have something where this is included, like this isn't, and then you have this. But the issue is every point here does not lie in the interior. No, so it's not so much about including 0, 0, because it won't include that. We're starting with the space without the origin. It's very much that these points, not in the interior. And so this set isn't open. It contains points that are not in its interior. So it cannot be open. So yeah, it is basically open arcs. So you have the subspace topology. Okay. Cool. All right. So the next one, it seemed like people had down pretty much. So we started with 0, 1 cross 0, 1, right, our unit square. And we wanted to see how do we glue things together? Like, what do we make equivalent to get the torus, the Mobius strip, and the Klein bottle? Probably, yeah, I want to make sure I have the same picture that you guys were using. And I don't draw the wrong arrows. Okay, cool. So our torus, we wrote, well, I guess this one doesn't matter because I know they're just identified going the same direction. But the other ones, just to know which one I actually drew. Right. So again, every point is equivalent to itself, right? Because we want it to be an equivalence relation. So all points are equivalent to themselves. So it's really like, what are we adding? What are we really gluing? Because like gluing a point to itself doesn't actually do anything. So in this case, I mean, you look at something over here, and it has to glue over here. And we know the coordinates, right? Like this is 0 to 1, this is 0 to 1. And so what you have here, right, is when x is 0, at some y value, it is glued to the same thing at 1. So would it suffice to say all points are equivalent to themselves unless stated otherwise? Yes, if we're doing equivalence relations, yeah, you don't need to tell me that it's reflexive because it's an equivalence relation, so it's got to be. So I'm assuming this, yeah. 0y to 1y. Yeah, exactly, Nick. And then the red one here, right? This would be fixing some x value. And there you just have x0 is equivalent to x1. Exactly. Yep. Don't all the edges glue to one point, so you don't need to glue to any specific point. All edges glue to one point. No. They are glued to each other. They do not glue to one point. Otherwise, you would not get a torus. I mean, it's very much wrapped around, right? Like when you make the cylinder part, right, you glue the edge to the edge. You don't glue them all to one point. You still have length here, right? All right, cool. Yeah, so that's that one. The next one is Mobius. Get a pinch torus. Indeed. Is that a come on, bro? Oh, all right. So this is how I labeled this one. Okay, so yeah, what's going on here? So if I have some point, so these guys just stay the same, right, on the top and bottom, but on the sides we're doing a gluing. This guy gets glued over here, so if this is at height y, what am I gluing this to? So this is like 0y is glued to yeah, 1 minus y. Whoops, 1. Good, yeah, and then again, all points are glued to themselves. So it does not need to be the absolute value, although that is also true. These are all positive, right? So we're in the first quadrant. So y is between 0 and 1, and so 1 minus y will never get negative. Yeah. I don't have time to take your call right now, sir, but hopefully he has some info on why my Twitch failed me miserably yesterday. Okay. You know, they're in IT. I feel like they could figure out when I'm in class. But maybe that's just me. Okay, and then the last one, I didn't draw this, right? Let's make this one. Okay, yeah. Okay. So for our climb bottle, yeah, exactly, that is a torus. So for this guy, right, we have this same thing that we saw above with the Mobius strip, and then on the other part, we just have our original identification of x0 to x1. Right, so we're only doing the twist on one end and not both. All right, any questions on this? Cool. Sounds good. The sound of silence. All right. So, we've got one more before we start not doing examples of quotients. So here, yeah, this is something we did way back. I think that was chapter 0. Yeah. Indeed. So two ordered pairs are equivalent if and only if their y coordinates are equivalent. What do we get here? What's the result? What shape do we get if we twist both sides? It's a good question. If you twist both sides, it's something called RP2. It's called the real projective plane. I'm not very good at drawing this, but you should Google it. Yeah. It's actually super important, and if you are doing the classification of surfaces, essentially this is one of the very few things that can be involved in making like a two-dimensional surface. Yeah, but hard to draw. Yeah, that. Hard for me to draw. But it's a very, very important space overall, RP2. And RPN in general. Very, very important. Yeah, so what do we get here? So this is 181, I guess. So wait. The intersection of this. Yeah, I mean we don't. Yeah. I don't want to talk too much about the real projective plane because like projective things in general, we would want to talk about what exactly these things mean, and that could be like a friggin' section, like a chapter in itself is just like projective. I mean, it could be a whole class in all honesty. Projective geometry. Yeah, Mark will type out something useful because he's good. But yeah, so let's talk about 181 here. So this one hopefully wasn't too bad. What did we get here? We kind of talk. Yeah, exactly. It's like the Klein bottle, right? Like the Klein bottle is a two-dimensional thing, but it exists in 4 dimensions, right? So some of these things you just need more space to actually do what you need to do. Right. Exactly. It's cool stuff. Okay, so thoughts on 181? What do we get? Yeah, it's a copy of R. You can think of this as a projection, right? So like you're fixing some B, right? You choose your equivalence class, and then it's basically the line y equals B, which is a copy of R, right? You can think of this as a projection, right? You take the whole plane, we have y equals B, and we're just sending all of the things with the same y coordinate. Yeah. Oh, wait, sorry. You want to think of it the other way, right? They have the same thing, then they are equivalent. So all of the things on the same y value are equivalent. So really it's like a copy of the real line. You're doing horizontal cross sections, right? All of these are glued to, say, x equals 0. Sorry, yeah. Right, so basically you have fixed your y coordinate, then all of those things get glued together, similar to the ray thing, right? So everything on a horizontal line is glued. So everything on a horizontal line is glued. They're homeomorphic. Yeah, so we're actually about to get to this, right? So we're about to start continuity and homeomorphisms, and that's exactly for this reason. Correct. Yeah. Yeah, this is mostly just to gain an intuition for like what's going on, and then we'll get the rigorous. We'll get the tools to rigorously show that this is the real line after that. Because yeah, what you really have here, right, is essentially you can write this quotient space, your x star, as the equivalence classes of x, y, or sorry, 0y. I can just choose a specific x value, right, where y ranges over all things in R, right? So I'm basically taking all of my horizontal cross sections, and so this is really my space, but then I just kind of notice, right, I have a very obvious map to the line x equals 0, right? And so R given by the equivalence class of 0y maps to y, and then we would show that this is a homeomorphism, and then that would give us our very rigorous and formal equivalence between these two spaces. Is 1y in x star? Yeah, it's just the same as, well, not as I have written it. Right, but like, yes, it's in the same equivalence class as 0y, right, because they have the same y coordinate. So like 1y is equivalent to 0y. So these are the same equivalence class. So I guess, yes, it is in there. But it would be redundant. Yeah. 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 Elements don't have unique representations, and all representations are an X star. Right, yeah, that's how equivalence classes work in general, right? Equivalence classes can be represented by anything inside that class. So yeah, that's why we have to check like well-definedness of maps, right? So like this map, I would have to check that it's well-defined, but it's pretty clear that that's true, right? Because if I take some other thing that's equivalent to 0y, it would be some xy, and that would also map to y. So things in the same equivalence class would map to the same thing. Okay, yeah. Cool. Okay. Dope. So, I'm curious to see how people thought about the Hausdorff thing. So, because I think in general, coming up with counterexamples, I'm just kind of curious to hear your thought process. So we saw that subspaces of Hausdorff are Hausdorff, but we claim here that X Hausdorff does not in general imply that the quotient is Hausdorff. No idea. All right, that's fair. So this is where, I don't want you to try to think up something completely from scratch. I want you to think that, well, we have some examples of quotient spaces that we have seen from 170 to 181. Yeah, 171 would work. That is one. So like via 174? Is that what you mean? Sure. Yeah. So standard on R2. So 181 equivalence classes, we get the real line back. And I mean, yes, you'd have to check what the quotient topology is, but it is going to be like the subspace topology. So this guy actually is still Hausdorff. It's like R2 to R, and that R would still end up with the standard. But yeah, so I guess we use 174, right? R maps to essentially the digital line on Z. This is Hausdorff. This is not Hausdorff. We showed that a while ago, I think, or at least mentioned that that's true, right? Basically, you can't separate evens from the odds around them, right? That's the issue. So, 2 and 3, these guys do not have open or disjoint open neighborhoods, right? Because any open neighborhood of 2 must include 3. 171, Rippy said, that also works. So this was the map from R to ABC, where P of X, P90X, A, B, C, if X is 0, greater than 0, less than 0. So what can we not separate here? Well, again, as you might imagine, it's this point here, right? Because B was not open. So the only open set containing B is the whole set ABC. So B can't be separated in the Hausdorff way. There are no disjoint open sets around B and say A or C. It doesn't matter from A or C. We even had an example on our very first one. So you didn't have to go back to 171. You could have even used 170, and this is like your smaller counter example. And this is the one I kind of thought about. I just wanted like 2 points and not able to separate them. And so it's basically the Sierpinski topology, right? So, I mean, you can think of it as this, where again, I want the Sierpinski topology. So basically, I claim one of these to be open. So like say A is open, B is not. Then the only open set containing B is the whole thing. So then these can't be separated. Rip. And then again, so like a map you could use to do this would be P of X is A if X is negative and B if X is non-negative. These are all examples. is in the quotient space, the unit circle. You can have disjoint open sets for 0 and 1. Oh. I use 0, 1 with the subspace topology. That is Hausdorff. Its quotient is not. The circle is Hausdorff. You can't have disjoint. But 0, yeah. So that's the issue. 0 and 1 are the same point in the circle, right? So they're not two different points, so you wouldn't need disjoint open sets about them. Does that make sense? Okay, cool. Yeah, that's the weird thing about the quotient thing. Quotient topologies are hard. They take some getting used to, for sure. I mean, just like quotient groups. I mean, just gluing things can make weird stuff happen. Yeah. So I guess like having the examples already made it a little easier to search. For me, when I was coming up with it in general, like my way of thinking of it was really like the Sierpinski. It's a very useful thing for like counterexamples in general. It's very small and it's very simple and it's very non-Hausdorff, right? There are only 2 points and they can't be separated. And so I'm always kind of looking for like minimal things, and then I just kind of chose my map. I mean, I didn't necessarily have to do this. You could choose any Hausdorff space and just basically map it this way. Gluing is so random. There's no order in how you glue. It's just per your whimsy. What do you mean by that? I think these are pretty natural gluings in a lot of cases. I feel like a random gluing would be taking an interval and like, I don't know, gluing like, blue to blue and like green to green and like red to red or something. Like this would be a random thing to me. I don't know. But your mileage may vary. A lot of these are pretty natural. Random gluing seem yeah, I mean, very hard, right? Also, I don't. How would you define a we should talk after, but yeah, I'd be curious on how we should define a random gluing. I guess like a probability function on your set, and then in terms of whether they are 2 points are glued or not. But yeah, anyway, that would be interesting. What would that look like? Wormholes? I don't know, man. What do wormholes look like? Okay, so let's not go down this wormhole, and let's keep moving. Little blips. I mean, I don't know what this would just be, it would be weird. What are we even doing? We're moving on to continuity. That's what we're doing. So, continuity, important. Homeomorphisms, also important. So this chapter is a crucial one, right? So this is finally, like we ended up talking about isomorphisms fairly early, in fact, before we really talked in full formality about homomorphisms and group theory as a way of, saying two groups are equivalent because we're like, hey, these behave a lot alike. We would like to just use the one we know and love, like I just want to say every cyclic group of order n is just Zn because I like Zn, I know Zn, they behave the same. Why can't I just use Zn? You can once you have isomorphisms. So the same thing here, right? So as Devin pointed out, these are really like sets of equivalence classes, right? That sounds nasty. No one really wants to write every point as an equivalence class and like deal with everything like that and think like, oh, is this well defined? Is this well defined? We said that last one where we just like glued things, we kind of projected onto x equals 0. It's just the real line. That's something we know and love, hopefully. So homeomorphisms are a way of saying spaces are equivalent. But before we can define that, really, we need to know what a continuous map is. Okay, so a homeomorphism depends on that. It is a map that is continuous and has an inverse, which is also continuous. And so continuous seems important to first understand. So I'm curious, first of all, how many people have seen the epsilon delta definition. I'm willing to talk a little bit about that. Right, so f from R to R is continuous at A if for any positive epsilon there exists positive delta such that basically your error away from f of A is less than epsilon if you are within delta of A. Right, so basically this is a very continuous thing. So, I pick a point here, and then I want to make that black, actually. And then, my epsilon bound, I say, like, okay, this is my f of A. And so, this is f of A. And I'm going to go, like, epsilon gap on either side. Right? So this is epsilon. This is epsilon. And so what I need to find is the delta, basically how far I can go away left or right on the x-axis away from A and remain within this band, right? So like I kind of notice this and this, but delta is symmetric, so I kind of take the smaller one, and so it's like this interval down here, right? And so as long as I'm within this, down here in red, then I'm going to be within my blue strip up above, right? If I'm close enough to A, I'll have small enough error. And this works for any epsilon, so basically, shrink that error gap, then it's going to, you're going to have to change your delta. You may have to get closer to A, but you can still make sure you're in that band. Why do I start with epsilon? I'm setting my error bound first, and then figuring out how close I have to be to A to have that error, or less. I want to know how close I want to end up first. The if statement starts with delta, though. Correct. Such that, yeah, there exists a delta such that if you're within that, then you're within your error. Stability arguments? Yeah, you can think of it kind of that way, yeah. I'd want you to, yeah, I think in terms of what I think the word stability means colloquially, yes, that makes sense. But I'm not sure exactly what you were meaning by stability. You're setting up the if statement so that it's true by taking a true epsilon first. What do you mean by a true epsilon? I mean, you're just quibbling with like me having my if after? I mean, yeah, you could also do that. You could also say such that if this is less than delta, then this is less than epsilon. These are the same thing. Yeah. Like a small change in x means a small change in f of x. Yeah, that's exactly what this means. Yeah, that's exactly what this is saying. Yep. So have we seen this definition of continuity before, or like done limits at least? So I know like most of you didn't take calculus here. I don't know if any of you took calculus here. So how many people have seen epsilons and deltas before? Okay. Yeah, it usually is very challenging in calculus because it is like a foray into proofs. Got mentioned once. Yeah. So I mean, I think I usually mention like. Okay. Yeah, I usually draw this picture like one time, maybe without the epsilon, but when I talk about limits or continuity in my calc class, but here we don't really do epsilon delta. So let's just do a proof. Okay, so like let's take a function that we know is definitely going to be continuous. Let's just say we have like f of x is 3x plus 7 or something. So how do we show this is continuous? All right, let's actually prove this. I just want to show you an example of like how this stuff works. Quadratics are a little harder, and I try to walk you through that on the problem set. But I just want to see this one. Okay, so basically, actually, sorry, I'm not going to start with the proof. That'll happen after. You're basically going to work backwards to find delta, then write your proof going, then write your proof after. So basically, you're going to like run down like what must be true, solve for delta, and then when you actually prove it, you're like, okay, assume delta is this, and you just retrace all of your steps in the opposite direction, because you're kind of like working back. Delta is, so delta should never depend on x. This answers why you started. Okay, yeah. So essentially, you start by like, okay, we want f of x minus f of a is less than epsilon, right? Epsilon is, well, that doesn't really make sense, but I mean, yes, that is, it is, well, no, it's going to be epsilon over 3, not epsilon times 3, but the x1 minus x2 is weirding me out a little bit. Yeah, so f of x minus a is less than epsilon. Then we just translate, like, what does this mean? We know what f of x is, and f of a, right? So we've got 3x plus 7 minus 3a plus 7 is less than epsilon. Well, these guys cancel nicely, and so this is 3x minus 3a less than epsilon. I can pull out the 3, and it already is its absolute value. Really, you're pulling out the absolute value of 3 is less than epsilon. And so x minus a, and all of these are if and only if statements, right? This is kind of the key. And so you get this. And so basically, you just kind of run down what you want, right? You're assuming the end, which is something we normally are like, don't do this. This is bad logic. Well, it is bad logic if you're writing this as a proof, but it can help you kind of, reverse engineer the guy you want. Right, similar to like an onto argument a lot of times, right? You often like reverse engineer the guy that's going to map to your point. And so the epsilon is the change in f of x. Yes, correct. Correct, yeah. And so this guy should be my delta. Epsilon over 3. So now I'm ready to prove things. Right, because look back at my statement. I want to start with some epsilon, and then I need to find the delta that exists. But it's usually going to depend on epsilon. If it doesn't, well, that's what we call something different. Never mind. Okay, so let epsilon be greater than 0. You pick an epsilon. Yeah, be a constant. Then let delta, or define delta, to be epsilon over 3. Okay? Then if our gap here is less than delta equals epsilon over 3, we have this is less than epsilon, so this is less than epsilon. This is obviously poor form. I probably wouldn't write a proof just saying so, but this is what you get right now. And then lastly, you can just toss this in, right, because these are equal. Thus, f of x minus f of a is less than epsilon, and that's what we want. Okay, so that's your general process. For quadratics, you want to like factor them typically, but then you're going to have two things that have x and a in them, and that's where what you would usually do is take like a minimum. So basically, right, like I'm talking about things close to a, and so you may as well assume that your delta is no greater than 1, right, that you would take close things. And that's basically how you run into those arguments. So like the one on the problem set, you end up with like the minimum of 1, delta is the minimum of 1, and then some thing depending on epsilon and a. That's very common with quadratic proofs for epsilon delta. But this is stuff, so this is what you would see a lot of in real analysis. So I don't want to spend like a ton of time on this since it's mostly not what we're talking about. I did want to talk a little bit about it though, because we're going to say that this definition is equivalent to our open set definition. Yeah. You don't need to go into like function spaces and stuff, but I mean it's probably something you'll talk about in real analysis, why like all polynomials would be continuous, maybe proving like exponentials are continuous, stuff like that. But yeah, I mean, there are more general arguments. It's not like you literally have to go through one by one. You can build up tools that help you. Okay. Yeah, but you don't have to go, you don't need to hit it with like a hammer of like a bunch of function space knowledge or something, because you wouldn't see that in like a real analysis course typically, and you would be able to prove these things are continuous. So for us, so this is the more general definition, right? Like this was very much R to R, although you can talk about this really in any like metric space, which we'll talk about soon, but I mean, it is what it sounds like. It's a space where you have a metric, some notion of distance, and then, you can take like an epsilon ball around something and in your target space, and then have like a delta ball around something in your domain, right? And so that argument makes a lot of sense anytime you have some notion of distance. But if you don't, right, if we don't have a notion of distance, then we need some other way to talk about continuity. And there it's going to be about open sets and their preimages. Right, so definition in general, f from x to y is continuous if and only if for any open v contained in y, f inverse of v is open in x. Basically, preimages of open are open. That's the short and sweet way to say it. Okay. So, the first thing that we wanted to prove is this 185, right? So basically, why does it suffice to, instead of looking at any open, to look at basic opens, right? So the claim here is f from x to y is continuous if and only if let b be a basis. Sorry, I want to say that first. Let b be a basis for y. Then f from x to y is continuous if and only if f inverse of b is open for all b in b. Can't we just use theorem 12 or 17, whatever it was? I think it was 27. Yeah, we can just decompose the open sets into basic opens. Yes, that is one of the directions. I was seeing people trying to do something that was untrue on the other direction. So which direction does that argument work for? I agree. Theorem 27 is one of these. Is that right to left or left to right? We can also recompose. That's the issue. Yes, that's what I wanted to talk about. So I was seeing a lot of, okay, we know Sorry. So if V is open, V is equal to these unions of these BIs, and so F inverse of V equals, by our theorem, right, the union of the pre-images. So now, this way, right, if F inverse of BI is open, then the union is, right? This way, what I'm hearing is if the unions of these are open, then each piece is open. Is this true? My tone probably reflects that it's not. So can you tell me why it's not true? So let me show you something. So can you write, so we'd agree this is open? What do you mean by smash down? So this is even more general. So you don't even need to... But there's no quotient space here. We don't need... yeah, we don't need a quotient map or anything. And in fact, this is true regardless of a map. So I mean, I've turned this in terms of pre-image, but like this is a bigger thing, right? So like unions of open does not imply, or sorry, union of sets is open does not imply that each set in the union is open. Yeah, okay. So this guy is basic open. Whoa. So this guy is a basic open set in R. No. Here, we're assuming that the union is open, not that we were implying this, which is not true. Yeah, the other way, you're right. That was exactly the argument. No, the direction is not hard. In fact, I think people are trying to do the if and only if or something, all in one, and so ran into this like logical mistake. But no, the argument's actually very easy without using this. But like, why is this not true? I want to understand why this isn't true first before we actually just like prove the statement. Okay, sure, yeah. Yeah, that's true. I was thinking just like here I can write this as this, but yeah, basically you're saying like, take an open set, U is equal to the union of all points in it, the singleton sets. So that would say that these are all open, which we know in general is not true unless it's discrete, right? So, right, just because the union is open does not mean that its constituents are open. So, real proof. It's easier than you think. Remember that continuous means the preimage of any open set is open. B is open. Right? Just let B equal that V. Yeah. Yeah. Well, no, I mean that's important though, because right, like I mean, I was seeing it was a fairly consistent thing I was seeing, so I think it was very much worth talking about. I don't want people to operate under that assumption. No, you can, but that's the other direction. So I mean, like if or maybe can you restate that? Yeah. Its pre-image is open. I want you to think of it as the pre-image, not f inverse, just because yeah, it's not a function. Yeah, but that just seems like more work, right? Like I mean, it sounds like you're telling me that like these are open. Sure, yeah, f inverse of b is open, so f inverse of b is a union of basic opens in X if you have a basis for X. By like definition of a basis. So like yeah, you could break it up as this. But then like the issue, right, is that you don't know that f of all of these is still open. Right? Like these are different bases, right? Like one lies in Y and one lies in X. Like your basis is for Y. These would be like basic open sets in X, and you don't know that like f of I don't know, call them your AI in X. These may or may not be open in Y. Yeah. Alrighty. Well, it's past 11, so we actually got through a good amount. It was a typical Tuesday thing, so I didn't really expect us to get through all of this necessarily. And it's good to talk about the quotient topology. I mean, I want to make sure we take our time and try to understand that because it can be challenging. So we'll dig into continuity stuff more for next time. If you want to try 186, you are more than welcome. But I will prove that at the start next time that these definitions are equivalent, right? Because we have two definitions of continuity. We would hope that they mean the same thing if we're in R, and they do. So this open set business, the preimage of open sets being open, is equivalent to the epsilon delta 1 if you're in R. Otherwise, yeah, I'm going to go to the bathroom real fast, but then I'll be around if you want to use office hours, and I'll be around again this afternoon. Talk about project, talk about problem set, whatever.